In the introductory unit, you were introduced to the conception of HCI, what HCI is, and what it tries to do. In this unit we will look in detail at the why of HCI, why it is important, and why it fails to have the impact one might expect of it. Designing a system that takes into account its users and is easier to use is always going to be more complicated, time-consuming, and therefore more costly than designing a system that does not. Designing for usability needs, therefore, to be justified carefully, and, assuming that it's justified, designers need to be motivated to work in a way that ensures usability. We will look at justifications from 4 perspectives. If producing usable systems is a cost, then an argument needs to be produced to show that the benefits of a usable system outweigh that cost. We outline the productivity paradox, an economic argument that computers and information technology systems do not seem to pay for themselves. The productivity gains in companies that implement its system do not seem to significantly outweigh the cost of implementing the systems. The productivity paradox is controversial and has exercised computer scientists for over a decade. We look at the argument from different angles. There are arguments that the paradox does not exist at all, and it is merely a myopic use of statistics. There are compelling arguments that the paradox does exist, and that it is caused by systems being designed without sufficient consideration for the users of those systems. We then look at arguments for the cost-effectiveness of making systems more usable, as well as outlining some success stories. Whereas the arguments for developing usable systems may be made explicit and quantifiable in a business context, technology impinges on our lives in ways which may be much less tangible. Badly designed systems can lead to anger and frustration for their users and may reinforce technophobic attitudes. Only by understanding humans better can such detrimental consequences be designed out of a system. However, many of these issues are very subtle, take effect in the long term, and cannot be easily quantified and costed. We look at how designers are, or may be compelled to be, motivated to produce systems which are not detrimental to users in the absence of a cost argument. We look at ethical issues in design, where users have rights not to suffer unusable technology, and developers have responsibilities to respect those rights, as well as legal issues where usable systems may be required by law. Technological systems are now extensively being put in place in situations where the failure of the system can result in severe injury and loss of life. Whereas productivity is central to cost-effective systems, reliability is central to safety-critical systems where reliability describes and measures the likelihood that a system may fail with undesirable consequences. Human operators control safety-critical systems and are therefore, in effect, as much a part of a safety-critical system as the technology. An understanding of human behavior should lead to a system being designed which takes into account the behavior of its operators, and therefore is less likely to fail owing to operator error. We also look at ethical issues of responsibility. The failure of safety-critical systems may dramatically affect the lives of people completely external to the system. In many non-safety-critical systems, direct legal and ethical relationships can be established between developers, users of a system, and consumers of the services provided by the system. Safety-critical systems may impinge on a greater stage if you are knocked down by a motorist driving a hire car whose ABS brakes are faulty. Who is responsible? The driver for bad driving? The leasing company for hiring a defective car? The manufacturer? The subcontractor who developed the ABS system for the manufacturer? Or yourself for crossing the road while knowing that there are cars out there with faulty brakes? In many engineering fields, standards are proposed which products should aim to satisfy. Products which conform to those standards are held to have attained an objective level of quality and are therefore more saleable. Standards for usability are immature, controversial, and not widely used. Many developers claim that their products are user-friendly, but do not often explain what that claim means. Standards offer a way of objectively measuring a product for usability, and therefore a motivation for developers to make more usable products. These 4 viewpoints on usability are not exclusive. Safety-critical system typically must meet cost requirements, etc. Despite all the motivations for developing usable system we shall lay out, there is very little evidence of user-centered design being successfully used in the commercial development of systems. We conclude this unit by suggesting some of the reasons for this apparent failure. To implement a technology-based system is expensive, and the cost of doing so must be outweighed by some potential benefits. Typically, when an industry makes an investment in it, they expect a payback in the form of increased productivity. A system of production has inputs, labor, raw materials, energy, and outputs, the product. Productivity is a measure of the value added to the output of the system, a productive system being one where the value of the outputs is greater than the cost of the inputs. Productivity is therefore a widely accepted measure of how well a business is performing. Note that getting your employees to work long hours would not increase productivity because you are simply making your labor inputs more expensive. To increase productivity substantially, you need to work more efficiently, not just harder or longer. One would expect that the introduction of information technology into a system of production would be just such a tool to increase productivity. It automates many dull repetitive tasks, either doing away with the need for low-skilled labor and reducing labor costs, or allowing workers to apply themselves to more skilled tasks, thereby increasing output of quality product, assuming that skilled workers produce better quality products than unskilled workers. However, many economic studies in the United States have shown that the expected increase in productivity caused by the implementation of its systems simply has not materialized. This is the productivity paradox. Until 1973, productivity increased in the United States, particularly during the 1950s, where productivity increased quite dramatically. However, since 1973, through the 1980s, and into the 1990s, productivity in the U.S. has stopped increasing at such a rate. It has still increased, but not nearly so dramatically. This period has been precisely the time during which industry has heavily invested in information technology. Apparently, the economic measures are telling us that implementing information technology has been worthless. It has hardly affected industry's ability to improve their productivity at all. Indeed, in some of the more pessimistic studies, it is claimed that productivity has actually decreased with the implementation of information technology. Care needs to be taken with this paradox through. Just because productivity flattened out at the same time as implementation of information technology got underway, does not imply cause and effect. The concurrence of these two events may simply be coincidence. The flattening in productivity may be caused by many other factors, and it may be that the implementation of its systems has mitigated the effect. Landauer, 1995, traces this argument through looking at several econometric models which try to assign cause and effect to the flattening of productivity. The details are very complex, but the procedure is as follows. An estimate is made of what productivity is expected to be, and then the difference between expected and actual productivity is measured, and candidates, such as crime, pollution, etc., are suggested that might fill this shortfall. Landauer argues that total U.S. output is 1.5% below expectations since 1973, and that the usual suspects cannot be made to explain this shortfall. 1.5% roughly equates to $30 billion per year of missing productivity. Its investments yielded 13.3% less than expected, which over an average investment of $225 billion results in $30 billion. Landauer suggests that this is the missing $30 billion. The argument is compelling, but not a proof that investment caused the productivity paradox. One should always be very careful with such arguments, and hold in mind Benjamin Disraeli's famous maxim, there are three kinds of lies, damn lies and statistics. The productivity paradox seems to be a largely an American phenomenon. It reveals itself clearly in the American economic figures, but is less obvious in the figures of other industrialized countries. America has shown the greatest growth in the industrialized world in the last 50 years, not least because compared to other countries, it did not suffer the wholesale industrial and workforce devastation caused by the Second World War. Europe and Japan's economies were shattered by the war, and much of the late 1940s and 1950s were spent trying to recover. Economic figures for Europe and Japan were therefore completely altered to the extent that trying to factor out the effect of the war in the economic figures, i.e. trying to calculate how Europe and Japan's economies would have fared economically if it were not for the war, is completely impossible. It is not really possible to compare the economic figures of America with the rest of industrialized world in a substantive way. The productivity paradox is present in other countries' economic figures, but not in such a pronounced way as it is for America. We need to be clear about what we mean by information technology. Computerization has greatly improved productivity, where computerization is the complete replacement of a low-skilled job with automated machinery. The banks successfully replaced their accounting functionality by computers, and this freed up staff to improve the communications with customers. However, recent moves have tried to replace these communications by automated systems. Automated systems are not good at communicating with people, not nearly as good as people are, anyway, and therefore, it could be predicted that more recent moves to automate banking systems will not show anywhere near the productivity gains that moves to automate the bookkeeping functionality did. Which brings us back to the productivity paradox. Computers are very good at replacing people when the jobs that people do can be captured mathematically and are dull and repetitious, but when computers augment a job where it is used as a tool by users to help do their job, the benefits of doing so are much more ambiguous. The productivity paradox arises when its systems that require a large degree of input from their user population are implemented. Hence, the theory that it is an inappropriately small concern for users in the design of its systems causes the productivity paradox. We will return to this later. The productivity paradox has exercised the economics and computer science communities considerably, and there have been many arguments advanced that the productivity paradox is simply a statistical mirage. Productivity is a measure of how well an industry is doing, made appropriate for modern information technologies. Even though productivity has not increased, other measures of how well a company is doing have shown considerable gains. It has caused an improvement in how industry works, but economists may be looking in the wrong places for those signs. Productivity is a measure of industrial success, and it has been argued that it is no more than that, a measure that is useful when a production system has tangible inputs, raw materials, labor, and energy, and has tangible outputs, services, that can be sold with an explicit cost, or widgets that can be put in boxes and shipped to customers. Systems that have a considerable component typically generate products. and advantages that are much less easy to quantify than numbers of widgets in boxes. There has been much recent comment on the emergence of a knowledge economy, where the main product of a system is an improvement in knowledge for the system's consumers. Information technology is about storing information, moving that information around, and most crucially, translating information from one form to another. A successful IT system will gather raw data, process that data into information, and deliver that information to consumers in a timely manner and useful format, so that the consumer's knowledge is improved. Much play is made of the fluidity of such systems. Out-of-date information may be worse than useless, and the time window on when information may be useful is narrowing all the time. Until recently, stock market prices were reported daily in the financial press, and this daily update of information was considered appropriate for most investors. Now technology has allowed stock prices to be delivered to our desktop computers, or even mobile phones, that is accurate to the minute, and the daily update provided by newspapers seems archaic. Technology can offer these apparent benefits, and they are very difficult to quantify. They are likely to be beyond the scope of equations for calculating industrial productivity. Furthermore, the implementation of its systems may need to be linked with new systems of management within companies. Old industrialized companies tended to have very hierarchical structures, with major decisions made at the top of the hierarchy and fed down through layers of middle management, with less and less decision-making responsibility to the unskilled workforce, who simply do what they are told. Computerization has to a large extent removed unskilled workers, and information technology has allowed the skilled workforce access to the information necessary in order to make more responsible decisions. Therefore, modern company structure tends to be much flatter, with executive decisions dispersed among employees who have much more responsibility for themselves and their actions. This flatter management structure is well suited to its systems, and there is evidence that if its systems and flatter management structures are implemented at the same time, then there are the sort of productivity gains for companies that should be expected. If, however, new management structures are implemented without its systems, then productivity remains quite flat, whereas, if new it is implemented without flat management structures, then productivity actually decreases. This effect may be crucial to the productivity paradox. There are productivity gains in implementing its systems, but those gains may be obscured by old and outdated management practices and structures. Management structures may be much more difficult to change than implementing its systems. Management is essentially about the placing and responsibility for power within an organization. Flattening the management structure is about dispersing that power. In order to implement a flattened management structure, the executive must take the decision to disperse their own power, in effect to become less powerful in an organization that they may own or have considerable investment in. Persuading the executive to do this is notoriously difficult. The answer is probably, but it is unlikely to be as profound as an initial reading of the figures suggest, and it is unlikely to be wholly due to badly implemented it. But the evidence still asserts that it has not been nearly as profitable as expected, and it is technology that needs to interact with people that seems to be failing. Landauer's thesis is that computers are failing to add anywhere near the value that we expect of them. His solution is simple and compelling. Improve the usability of computer systems. Given the evidence for the need for improved usability on a macroeconomic level, we now look at the actual design of interactive systems. What motivates developers, and how that may bring them gains in the short term, but trouble in the long term. Software developers are very conscious of deadlines. The software market is very fluid, and developers feel they must get products out into the marketplace on time, above everything else. A fear of being usurped by competitors who get their product out before you and corner the market is ever felt and real. However, Cooper argues that this determination to get a product out, no matter what the quality on time, distorts priorities. In the long run, he argues, it is better to get a high-quality product out behind schedule than to get a bad product out on time. Missing deadlines and failure to ship on time are not as dramatic as often held in the computer industry. He cites, as an example, the handheld palm-top market. In 1990, the pinpoint computer from Geo was released, and it was supposed to herald the dawn of handheld computers. It did not, and 2 years later, Apple released the Newton to universal apathy. In 1994, the General Magic Link brought out a handheld computer that failed to kindle any dramatic interest. Finally, in 1996, the Palm Pilot was released, was acclaimed, captured the market, and still sells well. The point being that, even though it was 6 years too late, it is a well-designed and researched product that satisfies its users. A typical measure of how good a product is are the number of features that the product offers. I am now using an out-of-date version of Microsoft Word to prepare most of these notes. By a quick count, I can see 105 options from the menu system alone, each of which relates to some feature or other. Let us say that some of the menu options relate to the same feature, so at a guess, I should think there are about 70 or so features. Of these features I use at most 10, and I should say, I do not know how to use half of the other features and do not even know what the other features are for. More up-to-date versions of Word come bundled with even more features, none of which I would use. I have, in fact, been using Microsoft Word since 1990, and the only new feature that has in any way changed the way I do my word processing is real-time spell checking. All other features, buried away in menus, toolbar buttons, and other dialogues, stay there, unused. Adding features does not improve usability unless, firstly, those features are useful, and secondly, those features are usable. Furthermore, an explosion of features in a system is not neutral. You may think that throwing extra features into a system, at worst, does not affect usability, and may improve it by offering the user extra things to do. However, extra features clutter an interface, and may make it more difficult to find useful features. Also, the product becomes more intimidating to novice users. Features can be expensive to develop, but if they are not used, then that effort is wasted in the long run. The fluidity of the software market means that there is little emphasis on analyzing why a product fails. It is better just to chalk a failure to bad fortune and move on to another venture. The availability of venture capital means that it is easy to do this. Venture capitalists will put a little money into a wide range of investments and hope that one at least will be successful enough to make a profit over all the other failures. A little analysis of why a product fails, and it is typically because a product is simply not a useful tool, or, if it is useful, it is too difficult to use, will prevent failures in future. A lot of venture capitalists believe that there is no way to predict what will or will not fail, the unpredictable market, and are therefore just as likely to fund bad products as well-researched and target ones. A random activity is lightheartedly called throwing mud against a wall to see what sticks. The funding of many high-tech capital ventures follows very much this idea. Software products tend to go through several phases while out in the marketplace. Successful products iterate through many releases, typically as more and more features are piled in, but sometimes as genuine improvements are made too. Cooper argues that the real cost in the information age is not what you are building, but what you are not. If it takes 4 releases to get your product right, then this means you did not release 3 good products on the first release. The solution to all the problems we have outlined above is design, where design is an activity that takes place before anyone actually gets around to writing code. It is important to find and understand the problems that users have and then to design a system that will overcome those problems. It is then important